All right, chapter 17 is on reflections and mirrors. The first type of mirror we'll talk about is a plane mirror. Something very simple that we've talked about in the past is that when light comes in at a specific angle, we call that the incident light. It reflects at the same angle, and that's called the reflected light. A couple vocab terms you might see. Normal means perpendicular. You might remember that from math class, but normal means perpendicular here. So we can say the angle from 90 degrees from the incident light is equal to the angle to the 90 degrees for the reflected light. All right, two terms you're going to want to know is specular and diffuse reflection. Specular reflection is what happens when you have a smooth surface like a mirror. What happens is obviously then you get a good reflection like this where that incident angle is equal to the reflected angle. What happens when you have diffuse reflection is when you have a rough surface and light scatters in all kinds of different directions. The road is actually pretty rough, so when you're driving your car down the road, you know, the lights are bouncing off the road and kind of bouncing back to you. Well, what happens when the road gets wet is it smooths out, and a lot of the light, you'll notice that it's harder to see the road when it's wet as opposed to when it's dry, because a lot of the light then is just the light from your headlights is not reflecting back to you. It's just bouncing off the road and going forward. Okay, you might notice that at night if you're driving on the road, especially at night, and you know it's wet, and you're on a two-lane highway. The cars are driving the opposite way as you. The light from their cars is bouncing into your eye, and it's obviously much more distracting. You can't really see the road as easily. So light reflects differently off smooth surfaces and rough surfaces. All right, so here's an example of some of the properties of plane mirrors. It turns out that light coming from like a bird, for example, on this limb, reflects off of a plane mirror, for example, and we see the bird as if it's at this point. Because our brain basically detects these light rays and detects that they're diverging from one another, and then our brain detects that those all come from one image point. So our brain can't tell the difference, essentially, between a real bird sitting over here and a bird in a mirror. If we don't know the mirror's there, for example, it's a big, a huge smooth mirror that we don't know is there, it looks like the bird's right here, at this distance away from this mirror. So here's an example then of a candle. So here's the object, the candle, and here's the image of the candle. Now here's the formulas that I put on the formula sheet. We're going to use these formulas to do every single problem and to organize all this information. I don't have all this memorized, and you don't have to either. But for example, if you put a candle here, it's real simple with a plane mirror, because the distance that you put the object away from the mirror is the exact same distance that the image is going to be away from the mirror on the other side. So you're going to see a virtual image, it's called. So if you look at a plane mirror, here's the column that we're working with right here. All the information's there. So if the distance to the object is greater than 0, which it is in this case, let's say it's 3 meters, then it turns out that the distance of the image is exactly equal to that, but on the other side. So this would be like -3, but really it's just 3 meters in this direction over here. And the object is going to be the same size, so M stands for magnification. And the image is going to be virtual. It's called virtual because it's on the other side of the mirror. So it's not we're not actually seeing this image. It's a virtual image on the other side of the mirror. So here's the properties that I just gave you in that on that formula sheet. Okay, the orientation is going to be changed, and you can see that if you look in the mirror. I'm sure you notice that left looks right and vice versa. All right, next is curved mirrors. So first, concave mirrors. Here's an example of a concave mirror right here. Some quick vocab. This point right there is called the radius of curvature. Okay, and we're gonna find out that radius of curvature C right there is equal to, we'll call it R actually, is equal to twice the focal length. The focal length here is the distance. Obviously, that's like the focal length of the parabola. We're gonna learn that these mirrors work best when they're parabolic, because all the light rays that hit this will then reflect right to the focal point. And if not, you get what's called spherical aberration, which I'll show you in a second. So we'll call R this distance to the center, which is twice the focal length. We'll call this axis that goes through the focal point and the radius of curvature, we'll call that the principal axis. Okay, so here's some just quick examples then. Let's say you put the object right here, and the object, you put it in between the radius of curvature and the focal point, then what you're going to get is you're going to get a real image that's going to be inverted and magnified. And once again, I don't have all that memorized, but what I do is I just use this table over here. So we're dealing with concave mirrors, and we're putting the object in between the radius of curvature and the focal length. So that would be this one here. The distance of the object is in between the radius of curvature and the focal length. You're going to get an enlarged inverted image, and it's going to be a real image, as you can tell from this picture right here. All right, the next one then, you can go through these if you want, but if you put the object, I'm sorry, that's the same as these. Here's another one here. Let's say we put the object is right here. We put it outside of the radius of curvature. Then what we're going to have is the image is going to be real, it's going to be inverted, and it's going to be smaller than the original size of the object. And that's all right here now. So let me switch colors. Now we're putting the object at a greater distance than the radius of curvature, and what we're going to find is a reduced inverted image is going to be real, and the distance of the image is going to be in between the radius of curvature and the focal length. So basically what I'm telling you is you don't have to memorize anything. I'm giving you all the information you need for mirrors. I don't want you to have to memorize anything. If you want to know what's going to happen if you place the object in front of a concave mirror, for example, and you place it here, whatever this object is, you know what it's going to look like. It's going to be inverted, shrunk, and somewhere in between the radius of curvature and the focal point. And we also have equations that I'm going to give you in a second to get exact mathematical representations for that information. All right, so here's an example of application to this then. Telescopes, some telescopes, there's different types, but some telescopes have two concave mirrors, one here and one there. And what happens is light comes in obviously about parallel from the source that's millions of light years away, and it then reflects off these concave mirrors and then goes and reflects off another concave mirror at the other side, and then switches the orientation again, comes to our eye. Okay, and we can adjust then to get things into focus. We can adjust the distance between these two concave mirrors, and so that we can get these light rays to converge at a point that we can see the image of. Okay, a term that you're going to want to know is spherical aberration. That happens when you don't have a perfectly parabolic mirror. What happens is if this is a spherical mirror, for example, then these light rays don't intersect in a point, so you see a blurred image. So these light rays, you can tell, are intersecting at different points. If you have a parabolic mirror, then what happens is all the light rays intersect at one point, and you get a nice crisp image. All right, so here's the mirror equation that's on your formula sheet. The relationship between focal point, distance of the image, and distance of the object. Here's the magnification equation, which gives us a relationship between a proportion between height and distance that the images and objects are away from one another. And here's an example then. Let's say we have a concave mirror and we have a radius of curvature of 20 centimeters. Let's say the height of the object is 2 centimeters tall, and let's say that this object is 30 centimeters from the mirror, and there's a picture here for us. The question is, what is the image position and image height? All right, so first off, we're going to use this first formula right here because they gave us the radius of curvature, which is 20. So we're going to plug 20 in and find that the focal point now is 10. So now we have another piece of information. The focal distance is half of the radius of curvature, which is 10 centimeters in this case. Now we can use centimeters here. We don't have to go to meters because we're using all the same units. Now we're going to use this equation right here because that gives us a relationship between focal point, 1 over 10 equals distance to the image and distance to the object. So 1 over distance to the image is what we're looking for, and distance to the object is, in this case, 30. So this is the equation we're going to solve. We're going to subtract 1 over 30 from both sides, and this gives us 1 over distance to the image. So I'm going to get a common denominator by multiplying the top and the bottom of this one by 3. In this case, I get 2 over 30 equals 1 over distance to the image. Now reciprocate both sides, and you get distance to the image equals 15 centimeters. Sorry, that's supposed to be distance to the image. And they also want to know the image height. So for the image height, we're going to use this formula now. Now that we have the relationship between distance to the image, distance to the object, we know the magnification. So the height of the image divided by the height of the object is 2 equals the opposite of distance of the image, which we found was 15 centimeters away, divided by the distance the object is away, which was 30. So we can multiply both sides by 2 to solve this, and we get the height of the image equals -1 centimeters. Now what that negative stands for is the fact that it's inverted. So you can tell this thing's been flipped over and it's an inverted image. And we know that too because we're in this column right here where we've placed the distance of the object greater than the radius of curvature, in which case we're going to get a reduced inverted real image. So we can always check with our formula sheet to make sure that our answers make sense. You can have a virtual image with the concave mirror if you put the object in between the focal point and the mirror right here. Then what's going to happen is you're going to have an enlarged virtual image, as you'll see from the formula sheet from these equations that I have right here. You're going to have an enlarged virtual image if you put the distance of the object between the mirror and the focal point. So the last thing is convex mirrors, and they're going to work similar to concave mirrors. I mean different, but similar to, for our purposes, that we're going to find all this information in this table. Now we're dealing with this last column here. Turns out that with these mirrors, we're always going to see a virtual image behind the mirror, and it's always going to be reduced no matter where we put this thing, as you can tell from this column right here. Okay, it's always going to be virtual and always going to be reduced no matter where we put it. All right, but we can do a quick example of that. Let's say we have a convex security mirror in a warehouse. Let's say it's got a 0.5 meter focal length, so F equals 0.5 meters. Let's say a 2 meter tall, so the height of the object is 2 meters tall, and the distance of the object of this forklift is 5 meters from. We're looking for the distance of the image, and we're looking for the height of the image. Okay, distance of the image is this. We can use this relationship right here. So we have 1 over the focal length, 1 over 0.5, equals 1 over distance of the image, plus 1 over distance of the object, which is 5. So we subtract, we get 2 minus 1/5 equals 1 over distance of the image. Okay, so I'm going to multiply top and bottom this one by 5. That turns this into 10/5. And now when I subtract, I get 9 over 5. I'm sorry. So we can solve this for distance of the image by reciprocating both sides, and we get 5 over 9. We can then plug that once again back into this equation right here. So we have height of the image over height of the object equals opposite distance of the image over distance of the object. Now technically this is negative because it's behind the mirror. So that would make up our negative here. This would go back to positive. But the height of the image is what we're looking for. Divided by height of the object is 2 equals distance of the image, which is negative 5 over 9, divided by distance of the object is away, which is 5. I'll multiply by 1/5 instead of divide by 5, and I'll multiply both sides by 2, and I'll get the height of the image is equal to 5's cancel. This negative sign went positive, and we have 2 over 9. So the height of the image should be 2 over 9, and that's 2/9 of a meter. So this is the summary of all the information you guys need. It's on the formula sheet just like this. And as long as you have that, you should be able to answer any of these questions.